A single rose, a thorn will grow. Tell me your fears, they'll stay right here.
And you see immediately the paper then is burnt and catches fire and smoke comes from the beam. This is similar to what a high power laser would do in the field if the incoming missile were illuminated by a very high power laser.
The THEL is designed so that radar scans the horizon for threats. When it detects one, like an incoming missile, it will lock onto the target and calculate its trajectory. The THEL will then swivel towards the target and fire a high-powered laser beam. The beam is a few inches in diameter, but powerful enough to burn through steel. Within seconds, the intense heat from the laser will destroy the rocket in midair. This test, filmed on June 6, 2000, could determine the fate and the future of large-scale laser weapons. The THEL is about to attempt to do something no laser weapon has ever done. Shoot down a 122mm Katyusha rocket carrying a live 66-pound warhead and traveling at a speed of Mach 1. The moment of truth. The rocket is launched. Radar acquires the target. The laser locks onto it. The finger is on the trigger. But will it work? If so, how will it change warfare? And what if this technology falls into the hands of our enemy? June 6, 2000. White Sands Missile Range. The U.S. Army is carrying out a crucial test of a new laser weapon. It's the first trial to shoot down a live rocket in its 15-year development process. A signal is given, and in this actual footage of the test, the Katyusha rocket is launched. Radar locks onto it, the laser takes aim, fires, and in a flash, history is made. And we enter a brave new world. For the first time ever, a high-powered laser shoots down a rocket.
At that point, the general who was overseeing the test said, "We've just turned science fiction into reality."
Again, in slow motion, the Katyusha takes off at a speed of 760 miles per hour. After the radar locks on, you can see the high-powered laser illuminate the warhead. The temperature of the laser beam is over 1,200 degrees Fahrenheit. On contact, the laser starts to heat up the quarter-inch thick rocket casing. Within a second, the rocket is destroyed. Death and destruction at the speed of light.
The typical shot is of the order of a second in duration. That delivers enough power to the target that it explodes.
According to military sources, the THEL will operate at a per-kill cost of approximately $3,000, making it one of the most inexpensive anti-missile systems in existence. By 2025, the Pentagon is expecting 20 of these on its warships and another 100 on its tanks.
You're transmitting energy through the atmosphere and focusing on the soft spot of the target. And you do that all with a radar tracking and the telescope that transmits the laser light focused on the target for that short period of time to heat it up until you damage it.
It's the telescope that is one of the keys to weaponizing the laser. It's what keeps the high-energy beam of light from diffusing and losing its power as it streaks through the sky.
The atmosphere is not very kind to propagating high-power lasers. The laser heats the atmosphere and that causes the beam to spread out. But there are ways around that, and the ways around that were invented for astronomy, and it's called adaptive optics.
Adaptive optics is what gives modern-day telescopes their remarkable ability to capture startling images like this, instead of this. The fuzziness is caused by turbulence in the atmosphere, which fractures the starlight as it passes through it. Adaptive optics corrects this using a mirror. When a laser is fired, the beam is bounced off a special mirror made of flexible material, much like a funhouse mirror. Behind the mirror are thousands of tiny piston-like devices, which are instructed by a computer to push and pull on the mirror, constantly adjusting it to compensate for the turbulence and keeping it on a straight path until it strikes.